Okay, so here we go. Here we go on this. Okay, so today, listen up. Number one, we have our final math problems of the entire year. All right? No more math after this. 2, once we get done, as long as nobody objects.
I object. Sorry.
If you guys are good at doing with only 2 examples, the third example I'll print out and hand it to you, unless anybody severely wants to do that third example.
I object.
Well, I guess if Whitaker says, then I have to, you know. All right. I mean, if you do, just let me know.
I object to Whitaker's objection.
Oh.
I object to his objection.
All right. So on this process here, let's get underway with this. Electrolysis is still electrochemistry, except we have to have a power source because it shouldn't naturally happen. Okay? So, best way to explain this is through pictures. The picture on the left is what we call a voltaic cell, or it is often called a galvanic cell, which is what we've talked about up to this point. Look, it happens naturally. Electrons flow. You produce the electrons, which produce the electricity. Here, same chemicals, but you see this thing called voltage source. So a battery, you plug it into the wall. Extra power that does not come from the reaction. You force the reaction to move from your, in this case here, your cathode to your anode. So it's the reverse process because it has a power source. Now, this picture explains the differences very, very well. Number one, left side, that's what we've talked about so far. Galvanic, or sometimes we call that voltaic. They both mean the same thing. Over here, the picture on the right, this is our cell that we're dealing with, our electrolytic cell. Here's the differences. If you're not looking, pay attention to this. Anode on the left is negative. Anode on the right is positive. Cathode, negative over here on the right, but positive on the left. So we switch the charges. It's because we're forcing the electrons to go in a spot they shouldn't. The other difference is this. It requires extra power. Battery. You plug stuff into a wall. Extra power that's not in the chemical equation. So let's go through this. We're going to go through 5 quick processes. Okay? These processes are all large-scale chemistry manufacture process, all right? The other thing is they all require external power or external energy. So the example I've been given all day long is Chicago. Chicago has a lot more manufacturing jobs than anywhere else in the state. If you've ever noticed, you probably don't, but most of the state power plants send their power up to Chicago, not only because it has a lot of population, but 2, these plants take so much energy, so much power, because they're doing similar things like this. Not all do the same thing, but a lot of them have a similar process here. So first things first, we can get elemental sodium and elemental chloride if we take salt and we break it apart. Here's the problem. You have to put this, or you have to get this up to over 800 degrees Celsius, which is extremely hot. High temperatures require a lot of energy, which means a lot of power to make this happen. Now, in another type of process here, it's electrolysis of brine. Again, water, sodium chloride produce hydrogen chloride, sodium hydroxide. Now, if you're noticing too, I should have pointed this out on the other slide. You see this Y, this gamma looking symbol. Essentially, the book likes to put it, you could just substitute that out with an arrow. Okay, not extremely important. Now, here's something where it's probably helpful. It's probably something that you've at least heard of before. So you see those recycling cans or recycling aluminum cans.
Oh, yeah.
You see them all the time. So what they figured out, 40s and 50s, aluminum. The Earth has a lot of aluminum on the crust. Problem with that aluminum, right? If we would dig into the Earth, we'd find aluminum stashes. It's combined with oxygen. We have to get rid of the oxygen, heat that up over 1,000 degrees Celsius. So really, really hot, which again, a lot of energy, a lot of process there to get that aluminum separated for oxygen. Now, if we already have our aluminum and we're recycling it, a lot less energy. That's why there's such a big push to go through that. This requires so much energy, it's almost not even worth it to initially manufacture it. Okay? A lot of energy is in this process here. Now, same thing, we talk about ores. So you have like iron ore, you have, in this case, copper ore. Again, Earth has a lot of metals, a lot of available metals, but when you get them from the Earth, they're combined with other things, and we don't want that. Again, a lot of energy is used to separate these things out. Okay? Then our last thing here, again, another probably relatable thing. Has anybody heard of sterling silver?
Yeah.
Okay, heard of it. Heard of it. Sterling silver, it looks really nice, right? Here is what it is. They take a cheap metal, right? They make a fork, in this case, the picture showing. Then they coat it or they plate the outside with silver. In a very similar process here, obviously it's probably a little bit more refined. They don't use a lantern battery to throw on there. But it's a very similar process. What it does, take a cheap metal, you coat it in silver, you make it look nice so you're keeping your costs down, and it still looks essentially exactly the same thing. You just, instead of having a silver bar, you have a gold bar there. Yeah. So again, these things are very useful because they're seen every day. Now, here's our math part of everything that we've talked about so far, or everything we will talk about. One, we use stoichiometry, which we have used the whole year. We haven't used it in a little bit, so we'll remind you of what needs to get done here. But then, if you take a look where it says mathematical equation, we introduced this new item, Coulomb. It's really just a measure of electric force. I don't really want to get into that. It's more of a physics thing, but we need to know amps times seconds. Okay? Then 1 mole, we've dealt with the mole before, of E for electrons is equal to 96,485 coulombs. So now we're relating our new formula to our old stuff here. And just FYI, that 96,000 number is what we call Coulomb's law. And then one important part here, 1 volt, which volt should be capitalized, is equal to 1 joule per 1 coulomb. Does anybody remember seeing joule in this previous chapters?
Yes.
What chapter was it?
7.
Well, I don't need number, but you remember what topic?
Chapter 4.
There it is. Thermochemistry, aka what is happening with the energy of chemistry. Yes, very good. So relates 2 terms, energy and power. That's how everything ties together here. Okay. So chemistry really is all related. We can all talk about the things that I discussed the whole year. But let's do 2 problems. The third one I'll pass out. Okay. So problem number 1, it says a current of 5 amps is passed through a solution of copper 2 chloride for 1.9 times 10 to the 5th seconds. At the end of that time period, how many grams of solid copper can be produced? So let's go through this. And let's start with this. Copper 2 chloride. It's going to split right down the middle. Copper splits apart from chloride because it's aqueous. It's actually never really together. It's aqueous. And we get this. We get Cl with a minus charge. And the Cl with a minus charge goes to Cl2 gas. And because we have 2 Cl's on the right, we got to make 2 Cl's on the left. And then I ask you this. Okay, we got to balance out the charges, and we got to do that by adding electrons to one side, and we got to make sure they're the right quantity. We have a 2 times the -1 charge from our 2Cl-. We have a charge of 0 on that right-hand side. So what side and how many electrons do we need to add? Too easy. Plus 2 electrons on the right. Now, we go through our next process here, and we say this. Copper splits into this. We get copper with a 2+ charge, again, AQ for aqueous. It breaks and it goes into solid copper. And I ask you one more time, this is a 2+ charge, so be aware of that. How many electrons and what side do we need to add it to?
Right.
Yes.
I heard both. I'm going to clarify. We need 2 electrons added to the left.
Left.
Okay? Now, if you're writing this right, electrons opposite side, same number. Okay? So here we go with this. Now we have to use our new formula, which our new formula is going to involve these amps, and it's going to involve coulombs. So I'm going to write this down since we haven't used it. Coulombs is equal to amps times seconds. Do you see anywhere in the problem anything about coulombs?
No.
No. So we don't know. I'm going to put hashtag I don't know my number of coulombs. How about amps? Do you see anything about amps? 5 amps. Okay. So we have 5.0 amps times how many seconds?
1.9 times 10 to the 5th.
1.9 times 10 to the 5th seconds. A lot of seconds. So right now, all we have to do is multiply these things out. So we get 5.0 times 1.9 times 10 to the 5th, and I get 950,000 coulombs. So right here, this is 950,000 coulombs. The stuff that we just did up top, again, one formula is the new math stuff. Not horribly hard, especially since you'll be given the formula. This stuff right here, I know it's been a few days, is all stoichiometry. So we're going to do this. We're going to say times, and we're going to draw our line. What did I always say had to do diagonal?
Cancel out.
Cancel. So I'm going to put coulombs. I'm going to help you out here. On top, I need moles of electrons. So coulombs, the number on bottom. If we look for the number on bottom, what is it? 96,485 coulombs. Again, that is called Faraday's constant. Don't really need to know that. That's for how many moles of electrons? Good. Moles of electrons. Boom. Got it. We're still not at grams of copper, so we keep going. Now what cancels diagonal? Moles of electrons. If we're going from one thing, which we are, to another, on top, we want to go to solid copper, and I'm going to emphasize this with an S for solid copper, mole over mole. Where did I tell you to get that mole over mole number the whole year? Coefficients, perfect. So on bottom, we'll start with our electrons. What is our coefficient for electrons? Yep. How about solid copper?
1.
Very good. Still not in grams. Don't worry. Not a very hard thing to do. So we do one more step, and we say this, all right? Now, what has to cancel diagonal? Moles of Cu solid, or solid copper. On top, we can finally put grams of solid copper. We call this the what? Started with an, what is it? Molar mass. So we would look on the periodic table.
Oh.
On the periodic table, you would find that there is 63.55 grams to every 1 mole of copper. So all we have to do is just be careful and calculate it out like we've done pretty much the whole year. So 950,000 divided by 96485, enter. Divided by 2, enter. Times 63.55, enter. I'm going to round to the nearest whole number here. And so our nearest whole number that we get is 313 grams of solid copper. Okay? Again, not overly difficult. The only thing that we did differently is we added that new equation we went over today. Questions? Does anybody still need this? Good? Okay, one more example I'll show you, and then problem number 3 I'm going to give out to you, okay? So this problem says how many hours, that's time period, hours, must a current of 1.2 amps be passed through SN, which is 10,2 chloride, to produce 10 kilograms of solid tin. So here we go with this. Up top, I'm going to start out and I'm going to split this apart, okay? Now, we wrote down Cl in the last section, but did we even use that formula of Cl? No. So if you can knock that out, hey, knock it out. We're just interested in tin. So here's what happens with tin. Sn already has a 2+ charge. It goes to or gets reduced to solid tin. Okay, again, I ask you, how many electrons into what side do we need to get the charges balanced? Okay, 2 electrons to the left, and here we go. This time, it's almost, we're starting or we're picking up where we left the last equation. This time, if we're going to try to use this formula, amps times seconds, do you see anything about coulombs? No, don't have coulombs. We got amps. What about anything for a time period?
Yeah.
We don't have, well, we don't have it. We need to find it, it says. We are missing those parts. So therefore, if we're missing those parts, then we need to start with our grams, our mass. Now, I don't like 10 kilograms because that is essentially 10,000 grams of solid tin. So we're essentially starting backwards and we're going to work towards coulombs. So I say times, I draw my line, I put grams of Sn on top, and I'm going to have to go to moles Sn. Now, gram over mole, mole over gram, molar mass. Where would I look to find that number? Periodic table. The periodic table tells us this, that there is 118.71 grams to every 1 mole of our particular tin. Still not in coulombs, so we got to keep going. If we say times, we draw our line. What unit cancels now? Moles of tin. And I'm going to help you out here. On top, we have to go to moles of our E4 electrons. Mole over mole, where do we get those numbers? Very good. Coefficients. So on bottom, with solid tin, what number do we put with that? Okay. How about electrons? Good. Still not in coulombs, so we got to do one more step. And that step is cancel moles of electrons. And on top, we need to go to our coulombs. What number goes on top? Yep. We have our Faraday's constant, which is 96485 coulombs per 1 mole, and we turn to our calculators. Okay, so we take 10,000 divided by 118.71, press enter, times 2, enter, times 96485. Wow, I get a gigantic number. I'm going to put this in scientific notation. This right here equals 1.6256 times 10 to the 7th coulombs. Now, let's keep going here because coulombs equals, what's the first thing listed in our formula? Coulombs equals amps. Very good. We have 1.2 amps. Do we know how many seconds we have, or do we need to find that? Perfect. So we say times seconds. How do I get seconds all by itself? Divide by 1.2 amps. Divide by 1.2 amps. And when I do that, I'm still going to get a pretty large number. So I say divide by 1.2. I still get 1.355 times 10 to the 7th power seconds. Now, here is our final dilemma. We want our answer. We want our answer in hours. Does anybody know, if I set up the conversion, how many seconds are in 1 hour? Yeah, I'll give you that. Yes, that's it. 60 times 60.
3,600.
There are 3,600 seconds in every 1 hour. So I do one final thing. I say divide by 3,600 seconds, and I get still a big number here. I get, rounding to the nearest hour, 3,763 hours. Questions? All right, as long as nobody objects, I'm going to pass out.
I have, yeah.
All right, you want to do it with me? Oh, okay. I think he's good. I'm going to pass out problem number 3 all to you.
I object. Okay, now I'm checked.